Hello and welcome to, this is primarily for the people who don't come to our meetings, but hello and welcome to the Salem Athenaeum's Monday evening conversations. We have been meeting on the second Monday of the month for about 9.5 years, if you can believe that. Started in 2015 when Donald Trump started running for president in September. And many of us didn't think he had a snowball's chance in hell, but we're proved wrong. Our meetings really don't have an agenda other than considerate conversation about whatever is on our minds, and that can be many things. If you're interested in participating in a future meeting, just save the login information that you used to get here tonight. The following talk, A Brief History of Artificial Intelligence, came out of an informal discussion last month about artificial intelligence when Scott Guthery, one of our new members, had mercy on us and volunteered to give a talk on AI. As you can see from Scott's bio, included in the announcement, he is very qualified on the topic with a PhD in probability and statistics, past employment with many tech companies, a holder of over 60 patents, and a current researcher in figuring out how AI works. Time for question and answers will be available after the talk. Thank you, Scott, for volunteering.
My pleasure, Chuck. Thanks for the introduction. You've all heard about all the wonderful things that AI can do, but that's not what this evening's discussion is about. What we're going to do here is open up the hood and look at the engine and figure out how AI does all those wonderful things. And let me give you the spoiler for the evening talk. I took apart a lot of AI engines, and I built some of my own from the bottom up. And I kept looking for the mystery, the secret sauce. I expected to point to a particular line of code and say, aha, right there is where it all is. And I never could find that. What I was looking at was simple, very, very simple. And it finally dawned on me that that is the secret sauce of AI. It's doing a very, very simple thing again and again and again. So it's that simple thing we're going to look at tonight. So here's the basic setup for AI. For one thing AI does. So over on the left-hand side, we're going to be giving the AI engine a bunch of pictures of animals. And over on the right-hand side, there'll be a list of, let's say, 1,000 animals. And what the AI engine in the middle is supposed to do is, given a picture, compute probabilities for all of those animals, like alligator 1% and zebra 3%, and so forth. And here's a little bit in the middle. It thinks that that picture is a cat with 6%, and it's a dog with 17%. And what the training of the engine has to do is changing these dials so that it gets the right answer. And that is the core, the inner loop of AI, if you will. It's giving it some input, looking at the output, and changing these dials in the middle until you get the right answer. That's the simplicity of it all. So how does it go about doing that, you might ask? So let's follow up on our example here. We've given it the picture of this cat, and we've worked all the way through, and it's decided that the probability that that's a picture of a cat is 6%, and the probability that it's a dog is, let's say, 17%. So how did it get the 6%? Well, here's the dial that it used to compute the 6%, and the dial is currently set at 3. And its input came from the previous dial, which gave it a 2. So it simply multiplied its own dial setting times what it was given to get 6. And that is, you now know everything there is to know about AI. That's what it does. All right. So, but it does it lots and lots of times over. So how do we change that value for cat? Well, we can change two things. We can change the setting on the dial. So let's increase the setting on dial C a little bit. But we can also change what it's given. We can change the input. And if we change the dial a little bit, let's add 1.1 to it. And if we change its input by 0.2, then we multiply 3.1 times 2.2, and we get 6.82. So that improves its estimate of how much the likelihood that this thing is a cat. But where did it get the input? Well, it got the input from a previous dial. So let's go do it again. And that's the whole, that's how AI works, all right? So there's this whole cascade of these dials, and you can think of that as the columns over here, okay? So this is, I've made column C, this is column B, this is column A, and then so far on up. So in this very simple architecture, we've got an input layer, we've got an intermediate layer here, and we've got an output layer. And what we do is when we get the wrong answer, we just cycle back and we change dial C. Then we see we want to increase the output from dial B. So we'd go back to dial B. We would change dial B, and we want to increase the input from that it gets, and that's back up here. And we can't change the data, but we can change the setting of dial A. And that is how that's the inner loop of AI. Come all the way down here, get an answer, decide how you want to change the answer, and go back up this way, change all the input, go back down here, and see how you've done, and go round and round and round and round. And that's, if that's not simple, I don't know what is. I mean, that is just, and it's amazing to me still, after spending a long time in the guts of all this, that doing simply that simple can yield all the wonderful things we're seeing in AI. And let me just pause here for a moment, because I've given you the whole story here, in the first 10 minutes of the lecture. Does anybody have any questions about going around this loop? Coming down this way, and then going back up this way. Coming down this way, and going back up this way. Round and round and round.
Well, is it supposed to recognize the cat in the end? Is that the goal?
You're going to keep changing things until this percent is the greatest percent. Right? You don't care what the other percents are. All you care about is that the probability of a cat is greater than the probability of all of the other animals. So dog would go down to, I don't know what the outcome number would be. Let's say that cat ends up at 12%, and dog was at 9%, and zebra was at 3%, and alligator was at 1%. All you care about is that the likelihood of a cat, when given a cat picture, is the largest of all the inputs.
Okay.
And similarly, when you give it a dog, the percent for dog is the largest. And when you give it an alligator, the percent for alligator is the largest. So you're going to keep going around, giving it lots of different pictures. Okay, alligator, zebra, dog, cat, whatever, mongoose, and always tuning the dials so that if you give it a picture of a mongoose, the mongoose percent is highest. If you give it a picture of an alligator, the alligator percent is the highest. And keep fiddling with these dials until no matter what picture you give it, the right percent matches, the biggest percent matches the picture you gave it.
So it doesn't have to be 100%. It just has to be the largest percent of any of the choices.
Exactly. So you're not looking for 100%. You're going to pick the animal with the greatest percent.
So Scott, as we look at this, you've got a matrix here, which is, maybe 10 by 10. What are the real size of the matrices that we're dealing with here?
I didn't, I actually didn't pay that gentleman to ask that question, but here's the answer. Thank you very much for your question. So here are some terminology of this whole Grunsky machine, and some figures for the AI engines that are in play these days. You know, the Gamma and Llama and all of those things. Here's roughly a calibration of the size of those. So the network, that is to say, this whole network here, those are called nodes in the parlance of AI, and the whole thing is called a neural net. There are typically on the order of 10,000 dials and 25 layers, where each one of these things is a layer. Okay, so that's what the general order of magnitude size of the engines in play are.
Could, unless you're ready to speak, anybody, could you mute your microphones?
Okay, if that was a question, we can come back to it.
There's a little bit of magic that you elided over there, which is the magic in changing the weights, called back propagation, is actually quite difficult.
I'm not sure. Okay, let me, I'm not sure why it's difficult, but you're right. Back propagation is the name of the game. How do I go about making these things converge? If you're of an engineering persuasion, this is just a feedback loop. It's nothing more than the governor on a steam engine in some sense, done in the large. How you change the previous dial, how you change the dial previously, given that you want to increase this, is a bit of careful computation, but basically all you're doing is changing the parameters of the dials. So each one of the dials, while in our example here, each dial had just one number. It was the number that we multiplied by. In fact, in the big models, each dial has about 100 million settings of the dial, okay? And these are called the parameters. So there's 100 million numbers that you can set for each dial. And when you multiply that by the number of dials, when you hear that an AI model has 1 trillion parameters or 100 billion parameters, what it's referring to is the number of numbers you can piddle with to make it come out with the right answer. And the models in play today have about 1 trillion parameters. The process of piddling with the dials is called training. So what you do is you go back around and around and around and around, and you might ask yourself, how many times do you go around to change one of these models? A GPU is a kind of a special purpose computing engine, and that would take, to train one of the bigger models would take about 230 GPU years. That is to say, one GPU with given 230 years. Now, of course, the engines that are being built, I think one engine out there has 100 or 10,000 GPUs in it. So you can train the thing faster if you use more GPUs. The unit of compute is the petaflop, which is about 10 to the 15 floating point operations per second. So if you kind of put these together, you're going to go around the loop this number of times to train the engine. Now, the AI AI engines that you're using have been frozen in the sense that they've done all the training, and when you're using them, you're not changing the parameters. You're just using the ones that it's been trained with. So they're all settled down. Its training been done, and they're in production mode. And the other scaling parameter that we elided over here we had just one value coming down, one piece of data that we multiplied. That was the 2 back here. Okay, the 2 here. In fact, those are large collection of numbers, actually vectors of numbers, so that we represent the cat not just with one number, but with a bunch of numbers. Those are called the vectors of the AI engine, and those will be about 2,000 to 13,000 numbers long. So the things that are coming down here are not just single numbers being passed along, but there are these collections of about 2,000 numbers, or up to 30,000. And one last piece of jargon here. All of these things, each model that you see about in the newspaper has a different collection of numbers here, a different number of parameters, different number of layers, different size embedding vectors. Those are typically called the meta parameters of a particular model. So that's a rough sense for how big today's models are. Now let's go and let's ask the question, okay, all very well and good. This is how we trained a model to recognize pictures of animals. How about when we want to use this whole thing to do something else, okay? What do we change? Well, we change the input. We want to give it a picture of different things. We want to give it a real-time picture from a camera on a car, or we want to give it some text. So we change the input, and we also change what we regard as being the right answer on the output. And so for a AI engine that you might have had experience with, ChatGPT, the input is going to be a sequence of words, and the right answer is going to be the next word. Okay, it really is that easy. So give it words and try to predict the next word, and go around and around and around that loop until you're getting the next word in the text you're giving. And what I found surprising as I did some research is this is not a new idea. This goes all the way back to 1972, where a woman by the name of Karen Jones actually kicked this whole thing off. And it was the era where librarians were trying to automatically index journal articles. All right. So what they want to do is feed a journal article to a computer and have the computer say, okay, this is an article about, I don't know, alligators and diabetes. And that would be how they would index that article. And they give it another article and they say, okay, that's an article about, fungus and phases of the moon or something. So the whole emphasis back then, when computers started to be used for librarian kinds of tasks or information retrieval kinds of tasks, go back here where people were trying to take all the words in a journal article and boil it down to a couple phrases or words so they could index that article. The next step was taken in '89 by a scientist who is now unfortunately forgotten, Robert Heck Nelson, who really was the first person to work on the ChatGPT problem. And as a matter of fact, if you go look at his lectures, and they're on YouTube, he got the right answer. And as often happens in science, he was ignored by and large. But if I were to trace ChatGPT backward, I would chase it to this gentleman's work in the late 80s.
Well, wait. What about Hinton? Jeffrey Hinton did quite a lot in this. He developed back propagation algorithms.
Hinton?
Yeah, Hinton.
Do you have a paper? Do you have a date for the paper?
He's the grandfather of neural nets because he developed the gradient descent algorithm and the sigmoid thing that made back propagation possible.
I'll cover that in the history slide. You're absolutely right. I'll cover that work in the next slide.
And Newton, I don't believe, developed the idea of transformers. And the whole point of transformers is that you're not predicting the next word simply based on the words before, but you're doing it based on a matrix of all of the words before. That's what the T in GPT means.
It's given a sequence of words. It is sequenced because you do the placement. You care about how close a word is to the word you're trying to predict. Okay, so you're always predicting the next word. You can take the sequence as far back as you like, and Matthew, you can take it forward to get the next word. And the transformers is here in the fourth paper. So the third paper generalized the work of Karen Jones and went from simply indexing words to associating with a word a very long sequence of numbers called a vector. And this paper opened a lot of eyes because the classic example in this paper is that he produced a vector for queen and he produced a vector for king, and he subtracted the king vector from the male vector from the king vector. Well, anyway, I'm garbling it here, but there was an example in here where he actually showed that his vector space could be interpreted as representing words. And then the final paper, the gentleman referred to the transformer architecture that came here. And the insight here was that this is really all you need to do to realize ChatGPT, which is to pay attention to the words around the word you're trying to estimate. So let's take a look at how ChatGPT works. It's the same setup. Previously, you have all the dials. The input is going to be the quick brown, and you're going to run the dials until you get the right answer, which is Fox. So we have a list of about 50,000 words here. And what we want to do is give it the quick brown, and we want it to come up with the highest percent being Fox. And that is how ChatGPT works. Again, it is trained on lots of text and then frozen, and then what's made available on the public net is a model where all the dials are set and frozen, and you just go ahead and use the thing. I'm working with trying to dig into these architectures. I happen to be working with the Tom Swift books. Those may be familiar to some of you. Here's a particular book that I'm working with, Tom Swift and His Motorcycle. It's got about 1,700 sentences in it, about 3,500 words. I can train my ChatGPT on that text in about 5 minutes, and I can watch to see how long it takes the ChatGPT engine to converge to the right answer. So, and of course, once you have, if I give it Tom said that and try to estimate he, Then you give it Tom said that he, and try to estimate the next word, and it gets occasionally. And then you get Tom said that he occasionally, and estimate the next word, and it estimates did. So once you get going, you kind of bootstrap yourself into completing the whole sentence. And occasionally when you use ChatGPT, you'll kind of watch the words come out in spurts. And that's kind of why they do, because it's bootstrapping what it gave you just previously. Let me quickly, with respect to the gentleman's comment, let me quickly go into to at least one overview of the history of AI. There have been 3 generations. When people got thinking about let's build computers to act like humans, what we're so proud of course, is the fact that we think logically. So the first attempt was to build computers that thought logically. And that was kind of the first generation of AI. And what people soon discovered was that to get intelligent answers out of things like text, you have to come up with very, very large sets of rules, and managing those rules, getting the right set of rules for everyday things, for things like interpreting text, was very difficult. Now, they were absolutely wonderful for doing mathematical proving. That's exactly what you do in mathematics when you develop a proof. You have some axioms, you have some previously proven theorems, and what you got to do is grind away with plain old first and second order logic, and you prove your theorems. So that was wonderful at theorem proving, but it wasn't very good at common sense. And then the next generation said, all right, what we've got to do is start thinking intuitively. We have to somehow get common sense in here. But yet we still had to develop very large sets of rules. And the psych system, you may have heard the expression expert systems. This was the era of expert systems. And this was, I got my very first AI patent in 1989. And I have to admit, I was as clueless as everybody else, trying to develop big sets of rules. It didn't pan out. To capture what people did was to get an expert in some field and try to have that expert say, write down on a paper or through an interview process, tease out of that expert all the rules they use to come to their expert assessments of the situation. Now, it certainly is true that even going back before 1974, people had the idea of trying to model a synapse in a brain, where the synapses were connected, that they fed each other at different voltages. The voltages of the input, if the voltage reached a certain level, then they would fire and pass a signal off to the next cell. And indeed, the 2 gentlemen that got the Nobel Prize this last time out for their discovery in some sense of neural networks were working back in this era where we were trying to model individual neurons. And it's a matter of thinking about the history of science to know that today's AI architecture is exactly that. That we had the right answer back in the 50s, in the 40s, and it took us that long to say, okay, it's not thinking logically, it's not thinking intuitively. What we've got to do is model the individual neuron and its synapses, and that's what we're doing today. We're modeling in some removed sense, I guess, what we think goes on in the brain, and we develop these absolutely humongous neural networks. And of course, since we're doing something really simple, we can render the whole thing in silicon. And that's why, and we have every incentive to do it very, very fast. And that's why you see people developing AI chips. By the way, the interregnums here are sometimes called AI winters, where we kind of got lost and before we got regoing, we're in an AI winter here. So let me hang it out there a little bit and say what I think is on the frontier of AI today. Clearly, there's a new user skill called prompts, and in fact, when you use Google today, you might not be aware of it, but you're when you enter something in the Google window, you're entering what's called a prompt, and you just get back what you are inquiring about. But when you try to develop prompts for graphics, for videos, for songs, for lyrics, you can imagine the prompts get rather elaborate. And if you haven't tried out things like Midjourney, which is a great way to develop images, graphic images, if you haven't tried that, I encourage you to do so. But you describe the picture you want. You want an elf in a field sitting on a cow with green shoes on and a black hat and carrying a book of Newton's Principia. And it'll go away and it'll give you that back. And then you might say, I want to see that picture as Salvador Dali would have painted it. And it will give you back a picture of the elf in the forest with a copy of Principia as Salvador Dali would have rendered it. We've long ago passed the Turing test, which was can you tell whether you're talking to a computer or talking to a human being? And indeed, we have a situation now where people can actually develop friendships with ChatGPT characters in ChatGPT, and that's something we might want to talk about in our session. What do you do when people develop a friendship with a ChatGPT character and then you take the character away? Or what do you do when your toaster or your refrigerator learns all about your preferences, but then your toaster or your refrigerator breaks down? Are you going to want to retrain that new toaster or that new refrigerator? Another thing that is getting attention is undiscovered public knowledge, and what that means is we know things we don't know we know. All right, so out there in the literature, the classic example is out there are some papers about the fact that fish oil contains, I think it's omega-3B, and there are also papers in the literature that Raynaud's disease could be not cured but treated with omega-3B. But no one had put together the two things and say, well, if I've got Raynaud's disease, maybe I want to take some fish oil. And a fellow by the name of Swinson, Swinson, as I recall, was actually by hand. He didn't use AI, but by hand he made the connection between these two. It's something that we say, okay, we can treat this disease with this. And it was out there in the public knowledge. And one of the other things that we've noticed about AI, how it goes about things, is it will come up with wholly new ways of doing things that we haven't thought about before. And let me give you a couple examples. Sorting things is something that's been part of computing since I worked in an IBM data center back in the mid 1960s. Sorting things, there are literally hundreds of sorting algorithms. One had no idea that you could come up with yet another sorting algorithm. But when they gave AI a task of sorting things, indeed it came up with a new surrogate. It's come up with a new way of multiplying numbers. Mathematicians are from time to time surprised at the theorems, at the proofs that an AI engine will come up with for well-known theorems. So beyond just kind of mining, doing old things new ways, or finding out what we knew, what we didn't know we knew, there is, of course, the whole thing about finding wholly new things that we simply couldn't have done before. And chip design, AI, of course, is being used to design AI chips. And indeed, they're finding that the chip designs they're coming up with are not chip designs that human designers would have ever mastered the complexity of in order to generate. And I think the other Nobel Prize that was given for AI this year was for the two gentlemen at Google that made some inroads on the protein folding problem. This is, how do proteins in cells fold around each other, and that affects how effective they're going to be. Finding out the foldings for different proteins by doing lab work, and simply generating all the foldings in the lab would have taken a lot more time than was taken here. Quick look at further reading. If you here are just two of many books on the topic. If you're interested in the business angles of AI, I can at least point to this book, which has a certain amount of credence in the current reviews. And then many of you may be familiar with Stephen Wolfram and Mathematica. He's done a very nice book called What is GP Doing and Why Does It Work? A very small book, but I can call that to your attention. All right, I took a little bit less than the 45 minutes I claimed that I would take, but let's open it up now for discussion.
I've got a really basic question, which is how in the very beginning of the training do people who are programming these LLMs get it to determine, yes, this is the more probable answer? Like there's got to be some, I presume, either human input or looking at a large amount of data and looking for what the most common denominators are. Can you explain that a little bit?
Well, let's go back here. I give it a cat and it gets the wrong answer. I piddle with the dials until it gets the right answer. Your audio's off.
Who says that it's the right or wrong answer in the very beginning? That's the part that I didn't quite get.
Yeah, it's simply, if I take the answer it gives the animal with the greatest percent, it's clear that it got the wrong answer here. And what I want to do, what I know is the right answer is, if I look at all the percents for all the animals, I want the cat percent to be the greatest. So I keep going round and round and round until the cat percent gets to be larger than all the other percents. And that's how I've converged. That's how I've trained it.
So human beings are doing the training in the beginning.
Well, yes, a human being knows that this is a cat and it knows it's not a dog. And so it says we got the wrong answer. So I see what you're saying. Yes, there's a tag on this that says cat. And there's a tag on the picture of the alligator that says alligator. So it knows that this was the input. It knows that it was tagged to be a cat. And you're absolutely right. The tagging was done by human beings, presumably. And so given the picture and the tag that says cat, we can quickly say that it got the wrong answer here. So you're right. The tagging of the pictures was the human input.
And that occurs even with vast amounts of data that's gleaned from the internet. There's some manual process of tagging, or at some point is a part of the programming itself able to learn independently of human input and tagging.
Well, in the Chat GPT case, we simply have to say, we want you to get the next word. So I don't have to tell it what the next word is. I give it, I can say, the training sequence is the quick brown, and I've given it the sequence, the quick brown fox jumps over the lazy dog. So it can figure out what word without me saying the next word is fox. It says it's the word that I'm looking for, the word that follows brown. So in this particular case, when I'm doing text, I don't have to do human input for each right answer. The right answer is simply the word that comes after brown.
All right, so let's say, to go back to your Tom Swift book, you feed a collection of Tom Swift books into a not yet trained, but early stage being trained model.
Yep.
And then it understands how Victor Appleton put together sentences, and it understands the basic structure of Tom Swift stories, let's say. And then you say to it, write me a story where Tom Swift, whatever he encounters, his flying boat or something.
Yep.
And then it starts writing, I guess. And then it says, what would be the next thing that Victor Appleton essentially would have done, from what I've learned from the entire collection of Tom Swift novels. And it writes the next word, and it keeps checking in that bootstrapping way you described before. Is that sort of what happens?
Yes, and I'll elaborate a little bit that during training, I take in these 1,700 sentences, and I train it with. I take the first three sentences, the first three words of a sentence, and I train it to get the fourth word, and then I take the first four words of a sentence and train it to get the fifth word. And then I do that for all 1,700 sentences until it's always getting the next word. Okay. Mm-hmm. Now I freeze it, and now I can ask anything I want of that frozen engine. I can ask, and it will say, if I say, what did Tom say? It will say, Tom said. And then he'll go in here and predict the next word, the next word, the next word, on down the line. So the only change the only elaboration I would make about what you said is to be a little careful to separate the training of the engine from the day in, day out use of the engine. In fact, I wrote a book about I wrote a book about technology in Boston in the early part of the 19th century, and I gave a course on it. And rather than having all the students buy the book, I simply put the book into a Chat GPT, and the students can now ask questions of the book. And I guess I lost some sales in that, but that's okay. They can ask whatever questions they want of the book. I did that with a couple other books, and it works out. It's a nice way to, if you want to end up knowing what a book is about, that's a real quick way of doing it. Just put it in an engine and ask questions of the book.
And one last question for me, I'll let other people talk, but when you ask it a question that it's in a way novel, so you're asking it a question in your case that isn't in the book, but it's related in some way, and it comes up with some kind of an answer. I was a tester for Gemini and Bard before that, and it was wrong roughly half the time, no matter what I asked it in the early stages. And so I'm assuming I was asking it things that weren't quite in its data set, and it was trying to approximate. Is that what goes on?
Yes. So you put in some words, and it said to itself, given that sequence of words, what word would I predict is next? And that's all it did. All right, after it gave you, if you put in 7 words, it would say, okay, given these 7 words and all the training I've gotten, what would be the 8th word? And then given the 8 words and all the training I've been in, what would be the 9th word? And that's how it blurted out what it was doing mindlessly. All right, it's and you're absolutely right. It got way off the beam. Whatever you put in, it's doing its best to predict the next word based on the training it's been given.
I have a question.
Say again.
I have a question. I was interested in the comparison of the human brain and the AI, like the program. Now, the human brain has plasticity. In other words, the human brain can change, the neural networks change for various reasons. You mentioned that the AI, once it's trained, is fixed. So that means it does not have plasticity or the ability to change. Is that true? I'm sorry, do you hear me?
Yes, I can. And yeah, when you use Gamma or one of the ones out there, it is not in training mode. It is in use mode, so that all the values of all the dials are fixed. Now, the people that built that can put it back into training mode and train it some more. But it's important to keep in mind that the 2 modes that the engine can be in. It can be in kind of production mode where it's all frozen and you get what you get, or it can be flipped over into training mode, in which case you're going to say, I'm going to give it some more data.
Okay, but you're saying in order to retrain it takes a human. The AI can't retrain itself. Is that right? I'm just talking about, it seems to me that there's still a limit on AI in a sense, because compared to the human brain has plasticity. In other words, neural networks in the brain can change over time depending on various factors. And it sounds like the AI is limited because, okay, another human has to retrain it, but that takes another human.
It simply has to be left in training mode. So imagine that the AI in your refrigerator has been left in training mode, and that you're using your refrigerator and it's changing itself. It's in training mode. So and you're the human. You're putting things in your refrigerator, taking them out, and so it's learning. You're the human, and it has been left in training mode. It will go on modifying its parameters to adapt itself to you. So it's simply whether or not someone has flipped the switch between frozen mode and training mode, and nothing stops you from leaving an AI engine in training mode and letting it watch what's going on and adapting itself to the current situation. So yes, it takes a human being to flip that switch, but if you leave it in training mode, then the human being's activity, if you will, how they drive their car, how they use their toaster, how they use their refrigerator, whatever, will be perhaps unwittingly continuing to change these dial settings, and therefore the AI will go on learning about something. It will go on learning about you. So you're right. If you leave it, if you train it and then turn the switch into frozen mode, what you see is what you get. It's turned off all its ability to change the dials. But if you don't put it into frozen mode, if you leave it in training mode, then it will go on changing its dials. And indeed, there's actually a paper from just out from Microsoft a couple days ago, where they let an AI, they kind of said to an AI engine that was in training mode, go ahead and think about what you've got and change your own dials. So that is a possibility too. They certainly have for a while been using AIs to train each other. I mean, that's how they did Go, right? They just pointed two Go players at each other and stepped back and they beat each other up. But it's critical to keep in mind whether it's in training mode or not in training mode. Anything else? I just can't have been that clear. That's impossible.
I'm looking at that picture of the cat, and it's trying the AI is trying to determine that it is a cat. Is it looking at an image? So it's looking at the stripes, the angle of the head, how it's attached to differentiate it from other creatures? Is it using those kind of characteristics when it has the image?
Fascinating question. Fascinating question. And there is active research going on right now to try to address that question. So the data actually that goes the cat picture is made up of pixels. Each pixel says, which is a little dot in the picture, and the data is a number that says, what color am I? Okay, so in fact, I've used a picture of a cat here. It's actually about a megabit worth of real numbers that represents all the colors here. And that's what goes in here. So there is active research in asking exactly the question you've asked, which is, how did it figure it out? Now, one of the oldest applications of AI is reading envelopes. Used in the postage department to read the zip code on handwritten letters. Okay, and that's it's called the MNIST model. It's been around for, I guess, 25 years. It does a very good job. It's a 3-layer model, and people have gone into there and answered a question. They said, let's go to the first layer. What's it figuring out here? Let's go to the second layer. What's it figuring out here? And let's go to the third layer. What's it figuring out here? And you're absolutely right. The early layer identified where the lines were and whether they were straight lines or curved lines. I think the second layer determined what lines connected to what other lines. And the third layer actually made the decision that this is an 8 or a 3 or a 2 or a 0. So in that one very simple application of AI to read handwritten zip codes, it took a while to get in there and figure out what the layers were doing. And that is a very active area of research, which is to say, can I figure out at what layer, what concept at this layer is the AI engine resolving, if you will. A very active area of research, and I will post, when I post the slides, I'll include in there a pointer to a YouTube video that goes into that question at depth, which is, how do I figure out what concept comes into being as the data goes through the AI engine? A very probative question. You're now an AI researcher.
Well, let me follow up that so are they putting in X number of pictures of cats and somebody identifying these pictures as cats, and they're pulling data from all that those numbers of cats so that they can change the levers to determine if they see the features of the original, something called a cat.
So the answer is yes. They're starting with as we do in science, which is try to hold as many of the variables as constant as possible. So I forget what I'm not sure if there's a researcher doing animals, but that's right. You would give it lots of cats, and you would see how these dials change based on the cat on various properties of the cat. So this imagine this has already been set up. Right, I've tagged 1,000 cats and 1,000 dogs and 1,000 alligators, and the whole thing is converged, so it's getting the right answer. Now the question is, how did it go about differentiating the cat from the alligator? You know, was it the color of the cat? Was it the ears? Alligators don't have ears, but cats do have ears. Answering those questions is turning out to be very difficult, and you want to do that. One of the classic examples is it was in some experiment they were giving it pictures of dogs and wolves, and they were saying and they trained the whole thing, and then they asked the question, how is it differentiating the dogs from the wolves? And the answer was because the wolves were in the snow and the dogs weren't. So that's an example of asking the question, on what basis is it differentiating between these things? And it may not be because it looks like a cat, if you get my point.
But it's working at the pixel level when it's analyzing the image.
Yeah. The input is that megabyte of real, that mega whatever, that million floating point numbers that are the value of each pixel in the cat. And what you would ask is, okay, at what point does it take into account the color? At what point does it take into account the fact that the thing's got ears? That maybe that's way down here that the earness comes in, but it may be way back up here that paws or four paws comes in. I mean, I don't know what's going on, but that's the challenge. Is at each level, what is the concept that's being recognized here before it finally decides that it's a cat? And that's a real hard problem.
I think.
I'm sorry?
I think that one of the things we're conflating here is using a network like this for classification, which is a hard problem, especially when you deal with things like image data, which is just an array. With generative AI. And the amazing thing about ChatGPT and the equivalence of that is not its classification ability. What we're really talking about is generative stuff. Midjourney generates images, ChatGPT generates words. And the issue of generative AI is more the trenchant point that I think a lot of people on this call are interested in. And I think your characterization of it is great. That it's kind of like statistics on steroids. If these are the words that I've got, this is the next word that's going to follow it. And there's nothing more going on than that. But there actually is, because that's the transformer aspect of it. It's a little more complicated when it starts to generate words and it starts to use. It's not really training versus fixed use, because it's accepting the context of what you say in order to figure out how to generate what's next. I'd love it if you could say a little bit more about the generative aspects of that and because attention is what you need, is obviously the seminal paper in that area. You know, how it does that and how it uses the context. I'd love it if you'd say a little bit more about that.
Okay, so this is the problem it's trying to solve. Given a sequence of words, ChatGPT and the transformer is doing this. If you look at the input to the transformer, the query is the first 7 words, and the answer is the 8th word. So that's the basic problem. That's the definition of the right answer that even the transformer architecture is using. Now, you can say, okay, well, let's give it some more. Let's not only give it the 8 words before, let's give it the 8 words before the word we're looking for and the 8 words after. And then let's also give it the positions of the words. So you can change the data that's going in in the transformer. And you're right that I was a little brief in saying that these are just dials, right? They're more than just dials, and how you connect these things together counts. Okay, so in my little example, I assume that here that I assume that dial C was only connected to dial B. Okay, and it's being pointed out in the transformer architecture that you could actually connect dial C to dials here, here, and here. Okay, so the interconnectivity of the dials is a matter of design, and people have found very good designs that work, and the transformer architecture is an example. But if you open up the transformer architecture, what you'll find is a bunch of individual dials that are simply set at different values, and the connectivity of the dials can change, and the transformer does some very creative things. So and that paper is such a seminal paper because of how they connect the dials together, and that's how they build their transformer. But the individual things in the transformer are just these kinds of things. Okay, so if we drill down, even ChatGPT is built from atomic elements that look like these dials. But you're absolutely right. Creativity has gone into how you've connected the dials together, and how you move data through the whole engine. So you're right. I've gone a little bit too quick, and maybe I made it a little bit too simple. I don't mean to say that there isn't a lot of creativity going into this work. There is, but if you open up what these gentlemen did, that came up with the transformer architecture, the individual components of the architecture are what I've been referring to as dials. Does that help a little bit?
I think what's astonishing about a lot of this is that transformer architecture multiplies the complexity of the problem a lot. It makes it a much more difficult problem, and I think that part of what we're dealing with today and addressing with this is that computation has caught up with that. and that the scale of computation you can do to do that is what's one of the astonishing parts of that. It's it's nice that it predicts the next word, but what does it predict the next word based on? And it predicts the next word based on so many variables and the context that you've set for it to actually do that is part of it. And that's what's astonishing. You know, that you can snarf up the entire internet and look at what next words are likely to be, and then add your own context to kind of narrow that. That's what's astonishing, I think, you know, like in many ways.
It is astonishing, and I agree with you. And the fact that we're getting that kind of meaningful, I didn't use the word correct, but meaningful or interesting output from something as really simple as the transformer. But I guess I would say that the fact that we can build chips, and if you look at these chips, each of these chips, the fact that you can render this whole architecture in silicon says that the atomic element must be the same for lots of different kinds of problems. And I'm suggesting that the atomic, here I've called that atomic element a dial. Now you've pointed out, and you're absolutely right, that the real dials are more than just a multiplication. Okay, but the point is that whether you're doing chat GPT or images or video or whatever else, the nature of that atomic element, which, you know, for those who know a little mathematics, it's just matrix multiplication. All of AI is nothing more than matrix multiplication. And that's what goes on in each of these dials. Each of these dials is simply the multiplication of a vector, which is the what you're passing around, and a particular matrix. And that to me is astonishing, that you can get as much mileage as we're getting out of this architecture from such a simple basic thing as matrix multiplication. And that's why you can build chips that do it. If I build a chip that just knows how to do matrix multiplication, I can get all of this going for lots of different kinds of problems. And I can run the transformer on a chip that can do nothing more than matrix multiplication. And you're right. The fact that we get such copious and bountiful output from this, from such a basic idea, is, and you can see why people are going in there and saying, you know, how does it do that? And Wolfram's book touches on that a little bit. It gives you a little bit of feeling for how it's doing it. But there's a lot of open research asking exactly the question that you're asking, which is, you know, why can such a simple thing, or maybe your question is, how come this architecture, the transformer, where is it, wherever it is, this architecture, the attention is all you need architecture. How is it that simple architecture can yield such amazing results out of such a wide, broad spectrum of problems, of voice, of driving, of movies, of videos, of songs? It is staggering. I mean, it really is. I agree with you. Quite amazing.
I think it would be helpful if you elaborated on exactly what a transformer is, because ChatGPT, the GPT, which is what it was before it was chat, is generative pre-programmed transformer. And so the transformer is a little bit more than just a straightforward neural net. And I think it would be helpful to explain a bit about what that word means.
I would be happy to, but that will be, I'd be happy to come back and do that, quite frankly. I can't do it here because I don't have a picture of the transformer in the slide deck. But I would be more than happy to come back for the second session sometime. Maybe not in the context of this discussion group, but to put together some people and walk through the details of the transformer. That's right. That this paper, there's a reason this paper is seminal in this whole work. But it is just, the transformer is just matrix multiplication. It really is. You have to,
Scott?
of course.
Oh,
I'm sorry.
when you're done explaining this, I do have a question. I didn't really know if you were done or not.
Go ahead. Yeah, absolutely.
Okay, so as a layperson, not scientifically oriented, I want to know that I can trust AI because it has so many applications in our lives, whether technically or culturally or literature or whatever. So this might be a simplistic example, but let's say we get either an X-ray, a CAT scan, or an MRI. And I have heard that AI can interpret and explain the results, even, and they see things more than the even a good radiologist could see. So how does it do that? And is that working on a very simple level, actually, within, the medical field? Is that like considered sort of a very small area of AI? And so now I have a little bit of education technically, and maybe if you explain what happens, how it analyzes one of these tests, I could now understand it better and trust it.
Okay. In the medical situation, the X-ray situation, I think the best way to think about that is asking another expert for their opinion of an X-ray. Do you trust that person? Well, I don't know. He's been right, he's been wrong, she's been right, she's been wrong. So it's that level of trust, right? It's another opinion. I would not hitch an AI engine up to a scalpel and just say, find out what's going on here and go ahead and cut the person up. So I wouldn't be willing to lie down on that table for sure. I don't think any of us would, but I certainly would encourage my doctor to ask an AI what they thought, or I would come home and ask it myself. All right. So in that situation, the input are tagged X-rays where a panel of doctors have decided that this X-ray does or does not show lung cancer. Okay. And I've got 10,000 of those over here, and I train this, and I want it to come out with 51% when there is lung cancer, and 49% or lower when there isn't. Okay, so that's how I would train that device. It knows those 10,000 X-rays cold. Now here comes the 10,001st, and it happens to be yours. Would I automatically trust it? I don't think so. It's never seen yours before. It's only seen 10,000 others. But on the other hand, when I call in my compadre, who is also an X-ray technician, he's probably never seen yours either. So, and I'll ask for opinion, and that person may say, I think there is or isn't. So I think that's the level of trust we're working with here is, do you trust it as much as someone that you'd call? I'm to the point where I'd say, yeah, I would want this opinion along with 3 others that I collected from human specialists in the air. But I think we're to the point where I would want at least one of the opinions to be from an AI engine.
But when you're with AI can scan like 10,000 X-rays of a similar problem. And obviously a human can't do that. Well, maybe in your career as a radiologist, you've seen way more than that, but you know, it simultaneously can scan all of these X-rays and sort of compare yours with those. And so do I know if my human expert can go through a similar process, or is it necessary for an expert radiologist to actually go through in their mind 10 or 20,000? Maybe they don't. I don't know. I am getting a little lost, but I'm trying to understand.
Yeah, I doubt that the expert has stored in his or her brain the 10,000 X-rays that they may have seen during their professional career. All right, so
Okay.
So there are 2 different ways of coming at the problem, and I think each still has strengths and weaknesses. Okay.
Okay.
I did make the point that what an AI engine is looking at to come up with its expert opinion, if will, may well be different than what the human X-ray technician thinks is important in those X-rays. It is quite possible that if we go in and say, how is the AI engine coming up with these very good estimates, we may find out that it's looking at something that the humans weren't even aware was there. A new way of gosh, we never noticed that if if it's black down here and black up here, that's an indicator too. We never thought that. I'm making this up, obviously.
Yeah.
But it is quite possible that the AI engine is keying on something that humans are not aware of being an indicator.
And so the humans can learn that there might be situations where the human experts can learn from what humans have put into AI and is all collected in the AI engine, that the human, in your case, can learn from that sometimes.
Yeah, and that's why it's important to ask. That's why it's important to ask that question. Why are you coming to this? What did you key on to come to this conclusion? Okay. And it may well be something. But down here, this undiscovered public knowledge, right? So that the indicator that it's keying on was there all along, right? In the very first X-ray was taken, it was black in the upper left and white in the lower right. Okay, and who knew that was an indicator for something? But we find that they keyed on, and if we can answer that question, how are you coming to that decision? We may indeed find a new way. In addition to the 17 ways we know, we now have an 18th thing to look for as human beings, and that's progress.
Okay, so this is my last question.
Yeah.
So that fox in the snow, it's not a dog. Oh yeah, the AI that figured, oh, if it's in the snow, it's a fox, whereas it might be a dog in the snow, right?
Yep.
So yeah, so it depends on what you key on. So I do understand in your examples of the black and white and x-rays that maybe there's a key that we didn't see or that was inaccurate, and it just gives us that input.
Yep. Maybe
Okay.
the technician held the slides a different way and left their thumbprint on it, right? Absolutely. It may be a completely something that had nothing whatever to do with a medical condition. It was just that X-ray technician always put their thumb there when the patient coughed and didn't put their thumb there when the patient did cough. I mean, I'm making this up, but
Yeah, but most technicians, just a few technicians might have their thumbs on it, but the other 9,990 didn't have a thumb on it. So you could sort of discount that thumb thing as an anomaly, I suppose. And that's something that the human judgment might also
that's
take
right.
into
And
account.
that's why you have to continue to ask the questions you're asking.
Okay.
Absolutely right. How did you come to that conclusion, right? And that it's hard to go into these big engines that we've talked about here and say, at what point did you decide, and based on what did you decide it was indeed lung cancer?
So people are studying this phenomenon. Experts in AI are studying this phenomenon in a general
I'm
way.
studying it
Okay.
with my Tom Swift here. That's exactly the kind of thing I'm studying in these little toy examples, right? How did it come to the conclusion that, and when it comes to JetPT, I'll tell you one other quick story. If you've ever wondered why, if you give it the same prompt, you get different answers sometimes. You know, when it's a computer, why doesn't it give me the same answer when I give it the same input? Well, that's because they're trying to make it seem humanoid, and if you ask a human the same question twice, you'll get a different version of their opinion. They won't probably say the same words again, right? Now, one of the things that'll come clear in that YouTube video I'll post is that it's interesting to ask, all right, it thought that the next word should be X. What was the next best word? Okay. And in that video, they used the phrase Wikipedia is, and then ask it to get the next one, right? So by and large, it came out with is trustworthy. But if they started looking at the second choices, they get words that were synonymous with untrustworthy. Okay, so now if I'm going to add a little fuzz in there, so it comes up with more human-like different answers, sometimes I'm going to get the answer Wikipedia is trustworthy or some synonym, and other times I'm going to get Wikipedia is not trustworthy or some synonym. So those are on the frontier of AI research. But that is a property of these. And so to answer your question, would I trust it? The answer is no. But that said, if it came up with something interesting, would I go, do I have enough faith to go and see if maybe it's come up with something I'm interested in? Yeah, I'd go. I don't think I'd be wasting my time, but I'd certainly as hell go check.
Okay, thank you.
Hope I helped.
Yes, indeed. Thank you.
Any other questions?
I think rags actually help with that trustworthiness.
And any subset of this group would like to get around and discuss the transformer architecture, I'd be more than happy to key up a discussion like that if anybody's interested. And it would just be, that I'd just be a bunch of us sitting around looking at diagrams and talking about them.
Based on that, if anybody would like to do that, they could email me their name, and I can get back to Scott with it. My email address is cvonbr@gmail.com, cvonbr@gmail.com, and I can coordinate that if anybody's interested.
Thank you. Thank you, Chuck.
Yep. Seeing as it's an hour and a half later, and most of the people on this call are probably over 50, some over 60, and tired at this time of night, maybe we should call it quits.
Thank you all for your attention. I enjoyed it greatly.
Yes, and thank you so
Yes,
much.
thank
It was
you.
really a great education. Appreciate it.
And
My pleasure.
attention is all you need, so thank you.
Yeah, thanks a lot, Scott.